Hello everyone and welcome to a new life hack. This is Patrick and today we will talk about meshing, specifically the surface to volume approach, which is a method that we usually apply for applications like structural mechanics or external aerodynamics. But there's a variety of applications where you can use this approach. The idea of today's video is to give you a brief understanding when this approach is suitable and what exactly it is that you have to consider, mainly regarding the geometry itself before you get started. So if I just go to my overview here, we will import and analyze our demo case, the geometry in Fidelity, and ensure that it is conformal. I will get to what conformal means in a minute. We will then modify this geometry in a way that it helps us during the meshing approach. Then we will prepare a rather simple mesh setup, and then go a little bit into the specifics like anisotropic edge refinement and proximity refinements. Also a very nice feature of the surface to volume approach in Fidelity. And last but not least, we will also include a few lines with Python during the geometry preparation in order to make you more familiar with the new Python API in Fidelity. All right, so let's get started. Before I jump into the user interface, if you are new to the surface to volume mesh generation in Fidelity, I strongly encourage you to take a look in the user manual and read a little bit about different aspects that you have to consider. I will cover some of those in the video today, but I won't be able to cover all of them. So be sure to take a look at this before you actually get started. All right, so let me jump into the interface. What we have here is a rather simple radial compressor, which will serve as our demonstrator today. What we have is several boundaries for each blade, and we have few boundaries that assemble the hub, the back face, and so on. The first thing that you have to consider before you get started with a surface to volume meshing approach is the triangulation of your geometry and to make sure that your geometry is conformal. What do I mean by conformal? Let me just show you the triangulation of this geometry, and then maybe it becomes clearer. So if we take a look at the leading edge of this compressor, you can see the edges of the tessellation right here. And as you can see, the edges that you see here, they do not connect to the edges here. So it's not really connected here. They don't have a partner. And the reason for that is actually quite simple. It's because they are actually a little bit too long. They are extruded into the hub. So they are not matching perfectly, which is in general not a problem. But since this is not a conformal connection, you will not be able to directly create a surface to volume mesh of this geometry. So instead, let me just check our example here. Let me also just maybe show the triangulation here very quickly. Here, everything is connected. So each edge here has a partner here, so there are no free edges or else. So this is a geometry we can work with, and we will in a couple of minutes. First of all, let me go back, and I will hide the triangulation here again. The first step that I'm going to do here is I will merge the solid bodies of the blades with the hub, because as you might remember, these are still separate bodies. They are not really connected with each other. They're just solids on their own. So the first thing that I would like to do is, and you will see this is about to fail, is to make use of a Boolean operation. So I will just select the entire geometry and go to this icon right here, transform, and say I would like to perform a Boolean operation and unite everything. And the nice thing of this operation is that if it works, it usually already gives you a conformal triangulation or a conformal geometry. However, this is going to fail. Let's just wait for a second. And it will give you an error message. Tool entities must either all be sheets or solid bodies. And the problem here simply is that the hub surfaces and the surfaces from the back, they are still considered as sheets in this case. And you can verify this or check this by going to Adapt Tessellation. And here you have this tool which converts cut to STL. And here it essentially shows you if a body is a sheet or a solid. So for instance, if I click on the blade, it shows me that this is a solid. So the first thing that we are going to do now is to sew all of these sheets into one single body. And this is something you can do directly here, also under Adapt Tessellation. You can just select all the sheets that you want to use, provide a tolerance, which I will define as 10 micrometers, and say apply. And now what has actually happened is that it sewed all these sheets together into one solid body, as you can see right here. And now I can, maybe let me show you something else. So if I just create a cutting plane right here, we can compare before and after in a minute. So this is what you saw at the beginning. The blades overlap the hub, right? This is something we see now on the cutting plane. And now I can select all the solids here and perform my Boolean operation. This is going to take a second. Boolean operation succeeded. And now the blades are merged with the hub and we have one conformal body. Let me just show the cutting plane again. And as you can see, as I drive through the body, now we don't have the overlapping blades anymore in this case. And also, if I deactivate the plane again, maybe let me just change the color real quick. We pull in the triangulation. Now every edge here has a partner, and we could directly start by assigning this geometry to a domain and start with our meshing process. However, before we do that, let me show you what our objective is. So here I have the final mesh. With the surface to volume approach, we can define proximity refinements to obtain this nice anisotropic edge refinement. But in order to do that, you have to, or you need two different surfaces in order to get this refinement. And this is why we will have to separate pressure and suction side from one another, because right now they are essentially, it's one surface. And so let me maybe just close this. We will not be needing this anymore. So I will just execute a script which will separate pressure and suction side here. In my case, essentially what we are doing, and we will cover this later, I take certain surfaces here and split them at a certain U coordinate. So I'm just gonna say run Python script. Let's see, code, split faces, And this is probably going to take a second. I will just pause the video here. So we just split the geometry into pressure and suction side, and I will now just group these surfaces. Therefore, I make use of this feature right here that allows me to select similar entities. So I can just press this button right here and then, for instance, select this surface, and now it will select all similar surfaces. So I can just group this now, and I'm going to call this, let's say, suction side. Then I take the pressure side, the fillets. All right, now I can just go to Mesh and create a new domain. Oops, I have to create a domain first. 1 second. This is probably something that is going to be simplified in the new release. But anyhow, I just created a new domain and assigned this geometry to it. Be sure to set some proper, oops, sorry for that, some proper location for the seed point. Now we can go to Mesh, create a new mesh setup, and now select the domain that we just created. In our case, I will choose Hexpress. Hexpress offers the possibility to use both a volume to surface or a surface to volume approach. Say close. And now I get this new icon here with a new mesh setup, and I can choose surface to volume mesh. Those are widgets right here that I don't need, so I use the turbo template, which is probably not absolutely necessary here. I can set cell size and use the preview in order to see if this size is appropriate. Let's see. Yeah, I think this is something that we can work with. So I'm essentially, the only thing that I'm doing at the beginning is I assign a global cell size. I will set some local values for the curvature setting here. 5 millimeters. That's it. So as you can see, there's actually not much to do. I mean, I basically just created the mesh setup, applied a global cell size and a value here. Actually, I'm not even sure if I have to go this fine. I will just save this for now, and then I can directly create only the surface mesh for now to accelerate this process. Yeah, I can take that. Let's just start this. So now the mesh generation is complete. Let's take a minute and analyze. So first of all, we can see our leading edge, yes, is more or less well resolved. We have exactly one cell here in the tip region of the blade. That is simply due to the fact that we chose a relatively large initial cell size. And since we did not apply any specific modifications except for that, so we applied precisely 2 mesh settings. We set here an initial cell size, and I changed this value for the curvature. That's pretty much it. So in order to get more cells in here, we will have to work with something that is called anisotropic edge refinement. And I will get to that in a minute, but first of all, let's take our finished project and compare what we actually want to do. So on the right-hand side, you see a very similar representation of the mesh that I just created. So we have one cell here, we have a relatively coarse leading edge. However, what we want is something like this. So on the left-hand side, you see the final result, which we aim for. So we want anisotropic cell refinement here, and we want anisotropic cells in the tip gap, or not the gap, but the tip region of the blade. So If you compare those two sides, this is something that we want to achieve, and that is something that we are going to do next. So let me just go back to our current status. And we will start with the number of cells here in the tip region first. Therefore, I just select the tip, and we have this nice option here where it says anisotropic narrow surface. I can just select that and define a number of cells that I want in this narrow region. So this will not work on any surface. There are certain rules that the surface has to comply with. Yeah, so it has to be very elongated compared to the width of the surface. But in this case here, it will work great. And I'm going to leave the default values here. Next, I would like to have the edge refinement here. And now we talk about proximity refinements. The idea here is that I can take two boundaries and say along this boundary I want anisotropic edge refinement. This is why we had to separate pressure and suction side before. So I can go to the proximity manager, create a new set, and now I can select suction side and pressure side and say create from selection. And now I could apply some settings here to define the first cell in, is it streamwise direction? So the coordinate here along the blade. I'm not really sure what the value was. Let me just check again real quick. Let's see. Proximity refinement, yeah, 5 millimeters. That looks reasonable. I'm sorry, 0.5 millimeters. All right. So let me go back. I'm going to add another 0 here. And that's basically it. So now between those two boundaries, the first cell in this direction will be 5 millimeters and then captured with anisotropic cells along the spanwise direction, combined with a growth rate here along the blade. So let me just close this, save it, and I will just zoom in so we can see directly how this is going to change. And I will just redo the mesh setup again, just the surface mesh at the beginning. As soon as we are satisfied with the surface mesh, we can take a look at the volume mesh. So I will just go to control again and redo the mesh setup here. Okay, so we are finished here. Let me just close this, take my tool, and here we have now the 5 or the 0.5 millimeters that we specified. And we have a nice anisotropic edge refinement here. And this is now something that you can do for multiple patches and boundaries. And also, I almost forgot, now we have 3 cells here in the tip region compared to 1 which we had before. And now, like I said, you could do the proximity refinements also, let's say, between the pressure and suction side and the fillet, between the fillet and the hub surface here, to reach what we have right here. So let me just maybe zoom in here. As you can see, we have more cells with high aspect ratio here. We have this angle here. This is probably something one could do a little bit better. But all in all, I think with some tweaks, you get very nice results here. All right, I think that was the main message that I wanted to communicate. Bottom line is, with surface to volume approach, for instance, for this application right here, you can reduce the cell count significantly compared to a volume to surface approach. You get or you can take advantage of cells with high aspect ratios, which is also something that sometimes can be very helpful. And yeah, so I hope you got the message. And Last, we will talk a little bit about a small Python script which you can use to separate surfaces in Fidelity. So, referring back to our initial state, what we actually want to do is the following. Transform, create curve. What we want to do is to separate these curves right here. So separate the blade surface into a pressure and a suction side. However, we want this to be precisely at the same coordinate for each blade, which it might make sense to use a script for this, and this is something that I'm going to explain now with PyCharm right here. So here I import the geometry library from Fidelity. I use the getTopAssembly method, or function that is, to get the assembly in the cut tree. And then I define a list of strings that correspond to the names from the surfaces that I want to split. So I'm not being very clear here, so let me just show you what I mean. I want to split these surfaces. These surfaces have names. So something phase 1, something phase 4, something phase 6. And what I'm essentially doing in the script is I define a list with phase and then assign the numbers. And then here I will search for the surfaces in this tree and tell Fidelity to split this phase. So I create this list of surfaces and then I loop over this list and use the function findGeometryEntity. And what this function does is it goes into the tree, into assembly, impeller, boundary impeller, and then looks for all faces that correspond to the name that I provided here. So in my case, it will search in this tree configuration for phase 1, phase 4, and so on. This function returns a surface, and then I can use this function right here to split this surface at a certain U parameter. And that's pretty much all there is. And like always, if you are uncertain about what this function does, be sure to have a good editor. You can click on it and then you get directly the doc string to help you understand these functions. All right, I hope this was helpful. Be sure to try it out, give us feedback, and have a nice week.